So thank you for joining this session. This is part of our Test Talk 2021. This specific day is about transceiver testing, and this specific session is about overcoming end-to-end testing challenges. So it's all about transceiver testing. And joining me today for this presentation is François Robitaille, NEMS Group Manager. Thank you, François. And myself, Gwen Amis, subject matter expert at Expo. And we've been at Expo more than 20 years each. So that's 40 years of experience right there at Expo. I want to start first with this technology evolution, and it's mostly about the standards. So if you go back in time, when we were doing 2.5 gig, 10 gig, it was mostly proprietary technology and development for transponders. And the manufacturers, the system vendors, in fact, they've been trying to get as much bit as possible per wavelength by increasing the electronic capabilities, the optoelectronic capabilities, and the modulation schemes. But the thing is, they were not compatible. So now that we are dealing with transceivers, of course, the transceivers need to be compatible and interoperable. So there is, in fact, we have some standards in the industry, the IEEE, the ITU. But what we've seen in the last, I would say 5, 6, 7 years is industry bodies or MSAs, so multi-source agreement, where you have a groupment of transceiver manufacturers, for instance, operators, users, and even standard bodies that are working together to build new standards. So the beauty with the MSAs in general, they are very specific for a specific type of technology or interfaces or application, and they are really fast. So they are really agile, so they can generate standards in a way that everybody will work on, or let's say develop the transceivers, and when we connect them, they will talk to each other, they will recognize, they will have the same protocol, of course, size, power consumption, shape and forms, and this kind of specifications. So of course, because of that, because they're agile, because they're fast, we need to adapt. So in the manufacturing process, when we have a production in place, if there is a modification or a new transceiver, we need to be able to implement those new standards fairly quickly. So being agile is critical. François, all yours.
Yes, thank you, Gwen. So one of the key disruption that we're seeing in the market today is really the people that are starting to use photonic integrated circuits or PIC to build their transceivers. You know, there are multiple advantages to go that route, so it's really fundamental. There's going to be really no looking back on this one. So lower size, smaller size, I would say, lower power consumption, better thermal management. So all the kind of things that people are looking for that are fundamentally coming with the integration of PIC-based devices into your transceivers. We see a couple of examples on the slide here. So if you're looking at some of the new technologies for 400 gig like QSFP-DD, say most of them are now PIC-based in terms of design. So what does it mean from a manufacturing perspective now of going that route? Is it changes the overall end-to-end manufacturing process and the way we have to look at it. So if we go to next slide, it's going to be easier for me to explain. Is, you know, before that you were buying components, you were buying a TOSA, a ROSA, you package that, you start testing it. The TOSA, the ROSA come pre-tested by the vendor if you buy them for a third party, and you really integrate this into a device. Now we're starting all the way back from a wafer, from a die, and we're going to be integrating that die with more or less complexity on it, more or less components on it. Right now, it's typically or optical or electronic. We don't have much of hybrid circuits yet, but this is definitely coming quickly too. So we have to test really the different parameters from the wafer all the way to the commissioning. And now the testing of those compliance to the MSAs, compliance to the standards may happen. And in fact, and you'd like to have them as early as possible in the process. And the reason for that is pretty simple. If we look at the bar chart on the left, with integrated photonics today, is it going to evolve over time? Most likely. Are we going to get to the same point as the silicon electronics? Hard to say. But today, if we look at the cost of packaging and testing a component after the wafer, it may represent 70 to 80% of the cost of the device. So as early as possible in the food chain or in the process, you can identify failures, means the more money you're going to save on your device. And in fact, indirectly, your device cost will be lower. So if we go to the next slide, one of the impact of that, and that's another way to look at it, is the quality cost. So just imagine a data center or an operator that would start deploying pluggables that would start failing one after the other, or because of a problem on a specific wafer, and you have all the same batch of pluggables that you start deploying. It's not only the cost of the deployment of the device itself, it's also the quality of service that you provide to your end user, the churn that you could get. So the the later you identify the problems or the failures, the more expensive they become, and that's typically exponential. So you have all interest to build a manufacturing process that is really looking at the end-to-end uh, testing and the end-to-end sequence, just not each step independent of each other. So starting with, if we go to next slide.
Francois, just
Yes.
before you jump to the next one, I had an experience, in fact, with some customers that were operators, and they were testing transceivers, and there are a plethora of providers and manufacturers of transceivers. So when you find an issue with the transceiver when you are a customer, this is the cost is not just on remanufacturing, retesting, revalidating, but also it impacts your name in the industry, and
Yeah.
that's a cost that is the highest, in fact.
Yeah. No, absolutely. Your reputation and so I say that then the customer churn increases for all kinds of reasons, and so the cost can become really, really high. So for operators, it's important that their suppliers provide good quality devices. So one of the important element that is starting to get into the our discussion and our philosophy of building test stations is really looking at, as I was saying, the process as a whole from one end to the other. So not only, for example, building a test station to validate to perform your functional test just before shipping, because yes, you can do that. But if you keep it and look at it only as an individual step, you're not going to be able to optimize your entire process. To be able to optimize that, you need to collect, gather data from every single step and be able to have good quality data that you can process, that you can correlate. So essentially creating ultimately in the best world, an automated feedback loop in your entire process where failures identified at commissioning would automatically have impact maybe on your wafer manufacturing. So, oh, hold on. If you do this, we've realized that it creates problems, so stop doing this. So, really creating ultimately a real-time feedback loop in your process. So, this is what we in the ideal world, what we would like to achieve. So if we get into a bit more details then on what do we test at each step and how can Expo help you in doing this, is really at the wafer level or the die level. Once it's cut, it could be to a certain extent you can perform some of the same tests. You have two ways to look at it. If it's an active device, then you're going to use an OSA. You're going to test your active device the same way you would do it with a TOSA. Ultimately, you're going to look at your power level, SMSR, things like this, right at the die level. However, if you have a passive device or a device that combines um, different components, you may want, or you will probably want to look at your manufacturing process, the wafer, to validate the performance of the various optical path. Then you do that in looking at insertion loss, return loss, potentially PDL of your optical paths. This is what's going to help you track down problems or in your process. If you have high insertion loss or high return loss, obviously this becomes an obvious indication that you have a problem. But sometimes it's not that trivial to say, well, am I at the threshold or not? You see a trend, but it's not necessarily clear. So this is why it's important at every step to collect the right data. But this is what you would typically perform at the wafer or die level. So if we go to the next slide, this is an
Francois?
example. Yes,
Sorry,
go ahead.
just on the
Yes,
previous
you go.
slide. Yeah, so you're saying that today, for example, that with the traditional transceivers and that use the legacy technology with OSAs, etc., we still use OSAs and similar methodologies. So what is the difference today with PICs? I'm sorry if my question is trivial, but
No,
what
no,
is
it's
the
not.
difference?
No, it's not. In fact, there are, when you have a TOSA, you have a clear input and output to your device. You have clear elements like the bias that you can control. It makes it obvious how to test it. When you're at the wafer level, depending on the coupling technique that you use, if you use edge coupling, for example, there are tests you won't be able to perform at the wafer level. So even if you have a transmitter assembly, but you use edge coupling, when it's on the wafer, there's no way for you to inject light. Sorry. So you'll have to wait until you're at the die level to be able to perform those more advanced tests. So how do you validate your process then at the wafer level is by looking at the behavior of the optical path, by looking at insertion loss or return loss instead of looking at active components. So that could be a fundamental difference in the two.
Okay, thank you.
Makes sense. Good.
Yep.
So coming back to this slide here, this is an example of a station that we've built, where you see at the top back of the station the T100 SHP and CTP10 systems that we offer to be able to perform those parametric, but not parametric, but insertion loss, return loss PDL test on the wafer, and it's coupled with a handling station and probing station from MPI in this case. And you see on the picture on the right, you see the wafer, you see the various dies, and how with the probes you're going to just couple with the optical probing and get some information on your optical measurement at the wafer level. So this is one example of a station where that you could use at the wafer level. Next. So now if we move along in the process, and we have two slides, parametric and functional tests, but those steps could be really multiple manufacturing steps, really. It really depends on the type of device that you're building, your overall manufacturing process. If you use a CM that will contract manufacturers, or that will provide you a completely packaged component, or if you do certain step yourselves, etc. But fundamentally, it's not going to change what you're going to do at the end of the day, where you have a transceiver PIC-based, you're going to want to do and test what on it. Same type of measurement that you would do on a discrete component base. Average optical power, central wavelength, drift, SMSR. So you want to perform the exact same test at this point. And if we look at the next slide, the functional test, which is essentially the last step before shipping, or really where you put the final stamping of your device. This is where you would do your bit error rate test, your transceiver sensitivity, your receiver sensitivity, sorry. You would stress your receiver for reflectance, measure extension ratio, things like this. So you have a completely packaged device now that you're testing. To get to that point from the wafer could be a couple of steps, could be multiple steps, as I said. But one of the important part is gathering the data for that. And we'll see in the next slide why, but you have to have some coherence in your data. You have to be able to correlate your data, as I said. So one of the approach is to build a test solution that combines tools that you're going to be able to combine together in a smart way, where the data you're going to be collecting at one step, you'll be able to match it with the data that you've collected at the next step. So matching equipment, matching instruments together, that will give you that capability. And we have a couple of examples here of what Expo offers in terms of bit error rate testers. You see the BA4000 on the left in the middle. This is really the tool that you're going to use to feed your electrical signal to drive your transceiver that you see in the middle. Some of the things you're going to do on the right are more of the measurements, the characterization, where you have a sampling scope. You can have a power meter to measure your output power. You can have an OSA. You can have the receiver part of your bird to do the receiver sensitivity. So all of this can be combined in a completely integrated station to allow you to get the high value data that you're going to need to automate your process, really. So next one, Gwen, I believe is all yours.
Absolutely, yes. The final step, in fact, of manufacturing in general, is the final test. So we validate. So we do the last commissioning. So we validate that everything is according to the specs. That the transmission power is good, of course. That the current is good. The temperature is managed. And to do that, and we do bit error test, of course, and we validate that there is no error. So to do that, we would have to insert the transceiver that is fully manufactured, in fact, into something that is as close as possible to the switch or the router or the network element that will support those transceivers. So to do that, we will use a solution like we show here. That's in fact an LTB8 with a 400 gig or two 400 gigs, 88460s. And we use a software called iOptics. So iOptics has been designed, in fact, to run exactly this kind of test. So it could be used, for instance, in final test, as well as the validation of transceivers from an operator point of view. So in an operator lab, for instance, or hyperscale lab, they can validate different kind of transceivers by using this kind of equipment to validate that everything is working flawlessly. They can run a test for long duration or under stress. So it's probably the easiest way, in fact, to validate that everything is working according to plan. Something I wanted to add also, it was about the data management. When you are running the final testing, that's where, if you find a defect, that's where the cost will be the highest. So we mentioned it before, but if you can correlate the data you're gathering from these final tests with the other steps along the manufacturing process, and you can correlate and validate that, yeah, there's been a degradation, or let's say the efficiency of the laser is not as good. You need more current to achieve the same output power, for instance. With that, you can validate and do some proactive modification in your workflow to improve, in fact, the yield of production. So that would be my final statement on this. So we do have a few minutes, in fact, for questions, if you do have some.
Yeah, I have one. I'm more from the field testing side, so I don't know how relevant this question is going to be, and I'm used to a system that is called TestFlow. I suppose you're aware. And the point that I want to make is you've shown different test tools like the bit error rate testing, and then you've shown also the scope, and you've shown other things. So what glues the whole thing in this end-to-end process? You're talking about data management. So what is this something that customers they have to integrate themselves? How does that work?
Francois, you want to take that one?
Yeah, I'll take that one. It's a good question to go in. One of the challenge right now is with PIC-based devices is the various steps of manufacturing is really performed by different companies, different entities. So you'll have the wafer being done at a foundry, for example, somewhere in maybe in Singapore, and then you may have a contract manufacturer in Mexico packaging your device for you, and you're an end user based in Europe or in USA. And how do you collect that data? How do you receive the data, and who? And even because you have third parties, you know, your foundry, for example, doing the wafer, and the CM doing the packaging, it means that those two entities would also have to exchange data to make the process optimized. So one of the approach, obviously, and this is generally today, if we look at the market today, this is generally managed by the end user. If we talk about pluggable, would be the pluggable manufacturer who's going to kind of implement his own tools to collect the data from the foundry, from the CM, will process the data or compile the data and process it. This is typically how it's done today. The drawback of doing that is that you almost have to wait until the end before you can feedback, because it's always dependent on the end user. So there's no direct communication between the foundry and the CM, as I was saying. So this is one of the, I would say, the weaknesses of what we do today, where being able to build a maybe some sort of cloud-based architecture where everybody would send their data could allow you, with machine learning, for example, to implement some machine learning capabilities to have a more automated process loop. So this is something that has not been really implemented in the industry yet from a manufacturing perspective. I don't know if that answers your question.
Yep, no, that's good, Francois. Thank you.
Good. Well, if we don't have any other questions, we'll have to thank you all for joining, and see you at the next test talk, in fact, that will be next week about 5G. Thank you,
everybody.